Hello, this is Z Mathematics, and today we are doing Corpio 2 hyperbolic functions. So let's just get into it. So in Corpio 2, we're introduced to these hyperbolics. They are really cool. They look quite similar to like normal trig, like sine, cos, tan, and all of that, but they're nothing to do with like triangles and like circles. They're not like waves like that or anything, but they are really cool. They're to do with exponentials. So let's just start off with this. So the pronunciations. This is shine, so shine of x. This is cosh of x, and this is either pronounced tanh of x or fan of x. So, or you could just say hyperbolic sine, hyperbolic cosine, and hyperbolic tangent. Doesn't matter. So these are kind of derived from exponentials. So shine of x is defined as this: e to the x minus e to the minus x over 2, or a half multiplied by e to the x minus e to the minus x. And this is an odd function, so f of minus x will be minus f of x. So shine of x is an odd function, and it's defined as this. Cosh of x is defined as e to the x plus e to the minus x over 2, or just written as this. And it's an even function, so f of minus x is just f of x. It has symmetry about the y-axis. And if you see here, this is just the average of the e to the x graph and the e to the minus x graph. I'll come to that in a bit when I show you the graphs for them. And then tanh of x, or hyperbolic tangent, well, just like in normal trig, how tan is sine over cos, tanh is shine over cosh. So what we get is, well, shine is e to the x minus e to the minus x over 2, and we're dividing by cosh, so we're just going to times by 1 over cosh. So 1 over cosh is just going to be 2 over e to the x plus e to the minus x, so times 2 over e to the x plus e to the minus x. These 2's cancel out, and what we just get is this over this, which is this. Now, because we've got e to the minus x over here, what we sometimes do is we can multiply by e to the x. So what we get is e to the x multiplied by e to the x to get e to the 2x minus e to the x times e to the minus x, which is just 1. And then on the denominator that becomes e to the 2x plus 1. So tanh x, or the hyperbolic tan of x, is this, which is simplified to e to the 2x minus 1 over e to the 2x plus 1, and this is an odd function. Their reciprocals are cosec, sec, and coth, or hyperbolic cosecant, hyperbolic secant, and hyperbolic cotangent, whatever you want. So again, just like in normal trig, you see hyperbolic functions and normal trig, they have so many similarities in terms of when we come to the identities and stuff like that. They are so very similar, and it's like really amazing how normal trig is to do with like triangles and angles and stuff like that, whereas these are exponentials and they're like linked. They are so similar. So just like normal trig, cosec is 1 over shine, which is, just flip this around, so you get 2 over e to the x minus e to the minus x. Sec is 1 over cosh, which is this, and coth is 1 over tanh. So these are the definitions of the hyperbolic functions. Now let's use all of this to try and answer all of this. Oops. So, shine of 3. Well, we know shine is defined to be e to the x minus e to the minus x over 2. Well, in this case, x is 3. So what we're just going to get is e to the 3 minus e to the minus 3 all over 2. Well, just using a calculator, e to the 3 minus e to the minus 3 over 2 is 10.018 to 3 decimal places. If you want to work out tanh of ln4, well, this time x is just ln4, so tanh is e to the 2x minus 1 over e to the 2x plus 1, so we're going to get e to the 2 ln4 minus 1 over e to the 2 ln4 plus 1. And this doesn't really need a calculator because we can use our properties of e and ln. Well, first let's simplify the logarithm. So 2 ln4 is ln of 4 squared, which is ln of 16. So what we can do is this is e to the ln 16 minus 1 over e to the ln 16 plus 1. Well, e to the power of ln something is just that something, so what we're going to get is 16 minus 1 over 16 plus 1. Well, 16 minus 1 is 15, and 16 plus 1 is 17. So tan, or hyperbolic tangent of ln4 is 15 over 17. Now if we have one like this, where we have cosh of x is equal to 30, well, what we do is write it out, so e to the x added to e to the minus x over 2 equals 30. So e to the x plus e to the minus x is equal to 60. E to the minus x is just 1 over e to the x. So we've got e to the x plus 1 over e to the x is equal to 60. So we'll multiply both sides by e to the x, so what we get is e to the 2x plus e to the x times e to the minus x is 1, so plus 1 is equal to 60 e to the x. Now if we bring everything to one side, we'll get e to the 2x minus 60 e to the x plus 1 equals 0. Now what do you recognise about this? This, hopefully, you should realise is a hidden quadratic. So we can just use the quadratic formula for this, and instead of getting x equals, we're going to get e to the x equals. So we're going to get e to the x is equal to, so we're going to get e to the x is 30 plus minus root 889. Root 889. So these are the solutions to e to the x. Well, if we just check what root 889 is, that is 29, so we can have 30 minus root 889 because, well, we know exponentials can never be negative. Well, 30 minus root 889 will be just less than 1, so it would be fine. So, well, e to the x is equal to this, so we can say that x is equal to ln of 30 square root 889. These are our solutions. So this is how to basically just use the hyperbolic functions, I guess, to like solve basic equations or find basic answers. So if I move this all over here, if we come back to the graphs, earlier when I said that like cosh of x is the average of e to the x and e to the minus x, well, if we just, I guess, draw a set of axes, e to the x is something like this, e to the minus x is something like this, never mind, e to the x something like this, e to the minus x is something like this. So what we're doing is taking the average. So we're going to start here and here, so the average will be like something like that, and it will get closer and closer here, and it will just go like this. So what we're going to get is, if you can kind of see, we're just getting like a weird kind of, not parabola, but like a kind of this sort of shape. So I've actually got a diagram of each of the things. So I guess this shows it a lot more curved, but here cosh of x, what I just said, was like this sort of thing. Here it's showing it as a parabola, but it's much kind of deeper than that. A parabola, this is more, it looks more like x squared or something like that, but the cosh graph is of like kind of a deeper parabola, like something like that. So yeah, so that's the graph of cosh of x, and you can kind of get it, like I said, from the average of this and this. You're gonna like start in the middle and like work it like that, and this is just the same as e to the x added to minus e to the minus x over 2, so it's the average of this and this. Well, e to the x is this, minus e to the minus x will be something like this. So if we take the average of this, like if we have here and here and we take the average, it's going to be something like this, and it's sort of going to like go through there and come out like that, and that is sort of what we have over here, this shine graph. It kind of looks like a cubic, very much like a cubic actually, but it just looks like this. And then tan of x looks like this, and their reciprocals. Coth looks like 1 over x, like that. Sech looks like a, I think it's called distribution curve, and cosech of x is again like a kind of deeper version of the 1 over x. And if you see here, there will be kind of asymptotes for some of them. So like here we won't have asymptotes because you can have any value of x, but here there will be an asymptote because this, we know it can't be 0, so e to the x cannot be minus 1. Well, we know that e to the x is like never negative, so that's fine. And there's going to be some sort of limit to this, and well, if x just gets very large, then, and well, as x tends to infinity, the minus 1 and the 1 will drop off, and then we'll just get this over this, which is just 1. So as x tends to infinity, tan x will tend to 1. As x tends to negative infinity, so for the tan graph, there are asymptotes at 1 and minus 1. And there are also asymptotes for here and for here as well. Anything with kind of radical or whatever on the denominator will have these asymptotes. So these are the basics to the hyperbolic functions.